Okay, hello everyone. Welcome to another Wolfram Language Design Review for our 14.3 series. I'm not in my usual location, so slightly attenuated. And Roger is sharing the screen, and we are looking at mathematical computation. This is a continuation of a review we started a few days ago, and we're going to tackle first non-commutative algebra.
Right. So we spent time looking at the thing that actually defines the algebra, which is this thing.
Right. But last time we were just digging into various issues about how to represent this.
Mm-hmm. Yes. And there is some similarity with the theory stuff, the proof theory stuff.
Theory, yep.
Yes, Roger, do you have the notebook I prepared on the relationship between those? If we need to, I can share that notebook. But
did you want to share that? We can do that.
If we want to go into the relationship between this and axiomatic theory, I can share that.
So it's up to you, Stephen. Are you with us?
We had some design things that we had flowed that we had done last time. Can we see how those have flowed through now and kind of start taking a look at how this is supposed to work? So last time we talked about.
Did you want to see the relationship to axiomatic theory, or?
Well, maybe, but I mean, I thought last time we had agreed that the main thing here is free algebra, right? That's the main case that we're dealing with here, correct?
Yeah.
That's the thing.
Well, it's the only case.
The only case, yeah.
Well, so why do we have the other things listed, like composition algebra and so on?
Because they have different operations.
Yeah.
Because the multiplication operator is different from matrix algebra and free algebra and composition algebra and so on.
So they're all free algebras, except that they have different names for the operators.
Right. Yes. So right. So you can customize. So just like in axiomatic theory, where you can customize the operators, you can customize the operators using an association here, but you can also customize the operators using these four named algebras, which will then basically set up the association for you to customize the names that are appropriate for that. But these are all, as currently implemented, these are all just different representations of the free algebra.
Okay, well, so it's been very confusing that there's one here called free algebra, isn't it?
Right, that basically corresponds to an empty association.
Yeah, okay, so but we need to give it a different name, because if they're all free algebras, then calling that one free algebra is confusing.
Yes.
Yes.
How do we name it? It's the one that has the generic non-commutative multipliers as the operator.
We could call it generic free algebra or generic algebra. It's not.
I don't know what's the operator name for composition algebra.
Composition, right?
Well, why don't we describe this as the operator, right? And free algebra is then non-commutative multiply. This one is compose, which a tensor algebra is dot. Is that correct?
It's tensor product.
Okay, fine. But name, just give the symbol name that is the multiplication operator.
So the matrix algebra will be dot comma n?
Yeah, I guess so. I mean, if we have to give the n there.
Right. Well, because for the zero element in identity, you need to know what dimension you're in.
Okay, fine. But I mean, but in general, these are dot, non-commutative multiply, compose, and tensor product, correct?
Yes.
Yeah.
Okay, so that's probably what we should call them. I mean, or have some way of. But I need to see a lot more stuff about what's going on here before we come back to this. But that will make it less confusing to have. They're all free algebras, but one of them is called free algebra, right? Which doesn't make a lot of sense.
Yes.
Okay, so let's keep going and look at the actual operations. And
okay.
I don't even know why we have to declare anything. This is.
Well, okay, you have commutative variables, for instance, and scalar variables.
We went through this last time, right?
Yeah.
What did we conclude last time?
Right. So we concluded that for simple things where you just need to like name the name the right. So when you give it an expression to do something with, you need to specify the operator. And so what we concluded is for those cases, you can just give the association with, multiplication goes to what your favorite
Guys,
operator.
the default is going to be non-commutative multiply, right?
Of course,
Yes.
Stephen.
Yeah,
But
so you don't so there's a case that we can do this in.
Yes, and all of the things have that case.
Okay, so can we see the minimal example? And in the minimal, even in the minimal example, do we, okay, so non-commutative expand, but get rid of the second argument there.
Right.
Get rid of the alj argument.
Yeah, so it's so
Get rid of that.
Use the default if you don't.
I understand. So please, let's see it without that. Okay, so we understand what's going on. Now, what is it assuming about A and B?
Nothing.
Nothing.
It's
So it's assuming they're non-commutative variables.
They are
Is that
non-commutative
correct?
variables. Yeah. Yeah.
Okay, fine. All right. So that's a nice non-commutative expansion with the decision that A squared is written out that way rather than it's A times A.
Right.
Well,
Yes.
This is not obviously correct. I mean, there are certainly in a bunch of operator algebra stuff, you don't usually do that. Just saying. Is it obvious that we want to do that?
I mean, maybe for the 2 case, but I would say certainly by the time you're at 3, you would always write it that way.
Presumably. Okay, but now the next question is it in fact, I mean, so how would I tell that whatever your non-commutative power, which is perhaps what we should call it rather than operation power, which I don't like very much, although I admit that non-commutative, there's nothing non-commutative about it by the time you're applying the same operation over and over again, right? But what it roughly is like if it's a non-commutative multiply, then this is non-commutative power, correct? I mean, it's the thing that goes with non-commutative multiply.
Sort of, but it goes with all the other operators as well, and the other contexts you can as well use it.
Right, and I don't believe it has, as currently implemented, I don't think it has a 2-argument form. I believe it always has a 3-argument form.
Yes.
But you need to specify what is the operation you're powering.
Yeah.
Although that could default to non-commutative multiply.
I guess
which is what you want it to do in these cases where you're doing non-commutative operations, right?
Right. Although we'd probably want the 2-argument form to evaluate to the 3-argument form just to canonicalization and
yeah.
So I don't like the name operation power at all. We had discussed some alternatives last time, hadn't we?
We call one idea was
generalized power. It was the idea then.
Yes, is maybe general power.
General looks good also, yeah.
I prefer generalized.
Generalized, okay. Yeah.
Yeah, general power is again like combatants in a war type thing.
Yes.
It goes with Admiral Plus, you're saying?
Yes, for example.
Yeah. Generalized power is good, yeah, I think.
Okay. So what's the relationship between generalized power and nest?
But
it's fold more than nest.
look here.
like
All right. We went over this last time. Yeah. So it's a k-1 fold. Is that correct? Is that correct, guys?
This was a K fold.
It's a
K
K
axis, K fold, or
Okay.
or
Okay. Yeah.
or-
All right. Fine.
or it's that there's k-1 f's. So
Yeah. Okay.
depending how you count it.
Okay. Fine. So let's just write, generalized power. What are you doing? I'm not seeing what you're doing here.
Sorry?
Okay.
I'm sharing.
No, I'm seeing. Yeah. Okay. Okay. All right, let's keep going.
Yeah, while we're at this, just one issue about, you can take it later on, but John and Jeremy are both here. There's a question about ligature, and maybe you don't do it now, later, the typesetting issue for this generalized power.
Well, it was about non-commutative multiply. You suggested maybe we
Oh,
have.
that's sorry. I'm sorry that yeah, I'm sorry about that. Yeah, that you won't do it now or later because I think.
Do we have people here who are relevant
Yes,
to
I thought
this?
if since they're here, yes, John and Jeremy were here.
Okay, so can we make the screen, okay, make it a bit larger. And then what we want to do is to have star star be some kind of ligature. Okay, so first question for you guys is what would be an elegant form? We talked about circle times. What would be, or just pure concatenation, what would you think of was the, what is a nice generic, thing to represent non-commutative multiply?
I mean, personally, I would probably use like a 5 or 6 pointed star. I mean, that could be convolution, but right. I think, obviously center dot is used, but that's obviously not evocative of star star. And that has so much other baggage in our system.
What about the
dot.
possibility of a small star with that's empty on the inside, so to speak, the outline of a small star?
I think that would be unique.
I would be concerned that it might be difficult to visually interpret.
As
I mean, we could just see it to be for sure, but I would have that concern.
oh well, what other? I mean, it would be nice if it was a Unicode character. Okay, and it would be, my assumption.
As in a standard, something that's in
Yes.
the standard.
Yes, I think so. It'd be nice if it was. John, do you agree, or is that not relevant to us?
I agree, but I mean, Itai's probably done much more of a search than I've been doing in the last 60 seconds, but I'm not sure that there is such a thing. I mean, unless we just kind of decide on a convention.
Well, there isn't a standard version of this, no. I mean, what I'm suggesting is this is a ligature. You type star star, it turns into this open, star thing. And then on serialization, it turns back into star star.
Right. So yes, we could certainly use right. I mean, right, that's no different than dash greater being, looking like rule, but serializing as dash greater.
Right, but the rule thing is our own character. Is that true?
Correct.
It's not a Unicode font character.
Right.
Okay.
So there is 273C, which is a 6-pointed asterisk around an open circle.
Let's try it. Roger, could you type that in?
I was trying to. What was it?
Backslash colon
not that. Type it
273.
type it into a notebook. Or to Wolfram Alpha.
Yeah, backslash colon 273C.
27.
3C.
Okay.
Okay, now make it a lot bigger.
Oh shit.
Just Alt plus.
Yeah, I'm trying.
Yeah,
I just didn't mark the right place.
It's amusing. Can you put that, A, that thing, B, at ordinary size? Well, make it a bit bigger than that. Bit bigger. A bit bigger, please.
I am doing it.
Okay. Stop. It's amusing. I don't know what other people think about this.
It's a very symmetric looking thing.
Which you don't like because it's non-commutative. I mean, I was thinking that if we had an open star of some kind that looked like it was kind of almost two stars superimposed, that would suggest the double star version that you type in?
So another possibility is, which is a close variant of that, is 2732.
You forgot the
The
colon.
Oh
colon.
yeah, I saw it. Saw it.
That looks more operator-y to me.
Yeah, so this is much more angular.
And Roger, I just mailed you. I'd listened to the recording last time, and I started to mock something, but it'd be a custom character.
Can you bring it up?
I didn't get it yet. You mailed it?
Yeah,
Okay. Not get it yet.
Roger.
I don't think it's a
that's-
big
yeah,
deal that it's a custom character.
I think
by the way.
you mailed it to the wrong Roger.
I did. I'm going to send it to you. Yeah, sorry.
Okay.
That's never happened before, I'm sure.
Right.
There we go. You should have it now.
Yeah. The thing that drives me nuts is S. Charon, right? Because obviously his email should be Sean C., but that's the wrong Sean C. as far as I'm concerned.
Okay, got it.
It's kind of the same character, but split in half. Trying to get both stars kind of in represented at once.
It's funky.
I think we'd want them closer together.
It looks wide, but scaled down to the size of a character, it really
Can you
smooshes up.
just drag that
Okay.
into a notebook, Roger, please? Now scale it down. Just click the thing. No, not the
Yeah.
cell. Just click the thing.
More?
Mm-hmm.
Yeah. I was judging it at the size of code. So about, that size. So it'd be half that size now. Right.
Can you make the whole cell bigger?
And now
no.
you need to rescale that.
It's not obviously crazy. Kind of something different. It's sort of a hairy something or other.
The other thought would be like a 5-pointed star, but rotated. So you've got 2 points on one side and 3 on the other and split still.
That's an amusing idea. I mean, what I was drawing was two open star-like things.
Yeah.
I mean, what about the possibility?
Yeah. Well, just quick question for John. Does the ligature have to be a basic box, or could it be like a rotation of a basic box, and then we could literally use star and a 5-pointed star and just rotate it? At least for prototyping purposes.
I don't remember exactly how we implemented it. I think it could be a general box, but I'd want to confirm that.
Look,
Okay.
what about something simpler in form, like a circle, like two, like potentially, because one of the common things for non-commutative multiply would just be a circle, right? But what about something where we've got like two circles, maybe of different sizes, offset against each other, making it clear that it's not symmetrical? Does that make any sense?
I think that would be even more non-standard than anything we've
Stephen, I think I
considered.
withdraw my sort of non-symmetrical complaints, because I think all the operations I've ever seen are symmetrical looking. Like composition is a ring and dot is a dot, and
right, unless you're doing set theory, right? Then you have things like superset and subset, right? If your model is literally
they are
sets.
very symmetric in that direction. I mean union or
well, yes, union and
Yeah, but
intersection.
subset
Yes,
And
greater than sign is not symmetrical, obviously.
but they are sort of suggesting order, so the order signs are not symmetrical, and this is not quite that.
All right. Well, look. So, okay, we're going to have a character. Maybe this is the one.
Okay, so it sounds like you want me to take these characters and play with them a bit as best I can, and
I'm thinking so, yes, and see
Oh,
whether we
okay.
can put it in as ligature.
Okay.
Now, okay, given that, what do we think the power thing looks like? The power thing could be this weird object with a number stacked on top of it.
Well, you mean as like an infix operator? Or because
No.
the standard form, right, is using the number, and then underneath the power, and then underneath the power is the actual operator you put in. So if it's non-commutative multiply, you'll get this one, and if it's F, you'll get
I see.
F.
All right, fine. Let's see that, please.
So yeah,
Yeah,
so do operation power.
Hold on.
Yeah.
I'm sure there are examples, right? That we can just scroll to. Yeah, here's
Yeah.
one.
Right. Or
Here's
the last one actually, right? That's showing different powers.
Okay, could you just type it in, please, for a second, because I want to see something. Just type it in.
Yeah,
Operation power.
Yeah.
F, comma, X, comma 3. Maybe we could just magnify this notebook a bit.
Right. And if you use a really long name that doesn't have an actual operator associated with it, it uses the first two characters and then a tooltip that displays the full
Can you
name.
try that? A, B, C, D, E, F, G.
Yeah.
For the first character.
And then if you hover over it, you'll see a tooltip for who.
Okay. I do think the 3 is a bit high relative to that. I think the 3 could be, sitting really right on top of that character.
Okay. I can adjust the spacing. Right.
All
This
right.
is just a standard underscript box. I'll need to stick in an adjustment box, but that's not hard.
Well, just be careful that it scales properly with the size of fonts and so on.
Yep.
Okay. Looking reasonable. All right. Should we go on? And then
Okay.
maybe we can let the graphics folk here leave, unless we have more to talk about with respect to how things.
I'm sorry, I was looking away because I was looking up Itai's question. Where did we leave things here?
I think in terms of the actual ligature is I'm supposed to look at these characters and play with them a bit more. So I guess I'll need Jeremy to email me that PDF as well. And we'll circle back to this. I think we won't make I don't think we've made a decision on the actual ligature right now.
Okay.
But that it's not critical that we solve it right this
Okay.
instant. Right, Stephen?
That's correct.
Okay, sounds
Okay.
good. I'll
Okay.
I'll email you offline then, Itai, with other stuff I found. So
Okay, cool.
Okay.
You
All
want
right.
to browse these functions?
Yes, let's keep going.
Okay. So collect is what it says.
So it has the same syntax as collect.
Yes.
So is that implicitly assuming some kind of scalar character to some symbols or something, or what?
Actually, the alg is the third argument. So this one you didn't give it, so it's the stock. Okay, so here is matrix algebra, composition algebra.
So that would be nicer to just be able to say dot as a second argument there. There's no n needed, just dot. Right? Do you understand what I'm saying?
Yeah, so this one would sort of not be enough, yeah.
Yes, it would be enough.
For some other cases where you actually may have to introduce 0 and 1, you need the n.
Well,
Right. So we
maybe,
either,
I mean, or we need a generic 0 and 1 that are, for any n.
But we want it to work with the matrix stuff, and there we want specific n.
right. It's
The
that
generic
symbolic
n are
right.
really bad things for doing the matrix operations. They mess up the dimensions of the thing.
Well, it doesn't know the dimensions in that case. I'm surprised we can't have.
But I don't think we have a symbolic identity array of unknown, of no dimension, right? It can be a symbolic dimension. But
Yes,
Right.
I understand, but isn't it always the case that when you use it, that its environment always defines what dimension it should have?
no,
Not quite. You can have threading.
Okay, but you can see the threading. It's not like it auto threads, does it?
No, but
No.
if you have something like 1 plus some symbolic matrix with no dimensions that you don't know what the dimensions are.
I'm sorry, I don't understand.
So you can add a scalar to an array, but the result will have the dimensions of the array. So if you didn't tell what are the dimensions of the array, then
right. So if you say, look, if you, I understand, if we support a purely symbolic identity of unknown size, then 2 times that is something we don't know what it is. Is that what you're saying?
Yeah, or 1 plus that or whatever.
Well, fine, but I mean, but okay, but 1 plus is okay, fine,
So
and the 1 in that case represents what? It represents a 1 in every position. Is that correct?
Yes.
Okay. So right now we don't have a way to represent. We've gone symbolic in terms of we can have n as the dimension of the matrix, but we haven't gone undetermined in the dimension of the matrix.
No.
But that's another level, right? To go undetermined in that.
Yeah, I don't even know.
Well, maybe it's not useful, but I don't think it's totally
I don't know what we
obvious
don't
that
know,
doesn't
so
make
to speak,
sense.
for that.
Right.
Yes, but so what is the problem?
So certainly in the, I think there are 2 points. One is in the context of the array algebra, right? We need to know, is it square? Is it rectangular? What rank identity array is it? Etc. So we always require, the arrays.
I'm just trying to clarify.
But
you need to know those things. Because why? Because if it's incompatible, you give an error message. I mean, why isn't there, whatever environment it's in, it just is the size it needs to be based on that environment? Is that obviously wrong? I mean, I don't understand. I don't see
in the same environment, a few sizes can fit, and it should behave differently depending on what are the sizes.
In what way?
Like you can do something if the expression represents a matrix.
No, not something you
has...
can do and you can't do, because that's what I'm saying. I'm saying if you can do it, but in 2 different ways depending on the size.
Yeah.
You know what I'm saying? Like a trace of an identity matrix is clearly the value of the trace of an identity matrix is going to be different depending on the size of the identity matrix, right?
Yes, for instance.
Right? Okay, so
yes.
I just want to know what things like that are there. Because clearly we could leave trace of an undetermined size identity matrix unevaluated.
Or we could return dimensions, maybe something of that sort, like, what would be the right thing.
I don't understand why that you need to do that. I mean, look, I'm skeptical of your claim.
If you are computing a derivative and you have the identity array somewhere there, you only are able to compute the derivative if you know exactly what are the dimensions of this array.
Because why? Because you're adding up all the different dimensions.
Because the result will have the dimensions appropriate for.
No, but that doesn't count, because that's not an issue. As soon as
Well, why not? If you take the derivative of the identity, array, NN, well, identity array of N, which is the N by N identity matrix, with respect to X, X, where X is a vector of length K, right? The result is O of N comma N comma K, right? It's a rank 3 array of dimensions N by N by K. So you can't differentiate, an identity array of unknown dimension.
Well, you get an O object of unknown dimensions. Right? Same deal. I mean, if it's of unknown dimensions, then it's O of unknown.
Why is it so important? I mean, I don't know. I suspect it's
well, it's not unknown. It's unknown K, right?
Yeah.
But why is it so important to?
Okay. Here's why. Because I don't believe in putting in irrelevant parameters. Well, in non-commutative expand, for example, I don't think we should have to say the size of the matrix, because there are many operations for which it's irrelevant.
Well, what if we
I think.
Well, do we have to put in the N, or can we put in the N or just matrix algebra and it uses?
It's not going to be matrix algebra. It's going to be dot. Because matrix algebra is completely obscure.
Fine.
Yeah, what we're saying is it's a structural operation, non-commutative expand, where the structural operation says it's this is the operator we're using. It's like distribute as an operator. It can be anything you want. It can be, foo if you want. See what I'm saying?
Right. I don't know if this is how it's implemented, right? But we certainly could have matrix algebra as a string, or dot as a string just work.
It's not a string. It's not a string. It's just a character. No.
Oh, you're saying
it is the actual operator. It is the actual operator. Just each one of these things, there's an actual operator. Compose, tensor product, etc.
Is that really
it's enough?
What we want?
It's enough.
I think that makes sense. Sometimes you collective route as well. You try and collect with respect to a particular operator, like basically. So
the only problem is how you can. It also specifies the identity. So in composition, it's identity. The multiplicative identity element. So for the matrix algebra, we would have to have the.
Right.
Wait a minute. Well, why isn't that known?
Identity matrix of unknown dimension and
I know that's what we were just talking about, right? That's what we're just talking about.
Yeah. So if you try to use it anywhere outside the non-commutative algebra thing, then it will not be that useful.
Wait a minute. I don't understand what you're talking about. This is a purely look. In the endless times
can I please finish my sentence, Stephen? That I've been trying for over a minute.
Go ahead. We're going to put a timer of how many minutes you're waiting to do a sentence. Okay, go ahead.
Right. So, we could. All right. So, if it's the symbol dot and not the string dot, I'm not sure I'm on board with that, but fine. Right. We could have dot and allow both dot and list of dot comma n. And if dot on its own needs the n, it could just use formal n, right? We certainly have things with default parameters when necessary.
Right, but the point that I'm making, rather forcefully here, is all sorts of times over the decades I've used non-commutative operator algebras of various kinds. Okay, and almost never do they have the official, formal, typed mathematical structure. Okay? Most of the time, it's just some, generating function, non-commutative generating function or something. And you're just putting out these terms, and you want to do what amounts to structural operations. You do not want to have to be very formalistic and say, I've got an algebra of this type, et cetera, et cetera, et cetera. You're just doing something which is essentially a structural operation.
So
And that's what we need to be
should
able to
happen
do.
if you have something like a dot this unspecified identity? Should it assume
Forget
that
the frigging identity. We're talking about things that say things like A dot, B dot, C dot, A dot, whatever. There's only dots there. What is the case where you're expanding things with dots? You have parentheses and you're getting rid of the parentheses. That's a very well-defined operation.
Right, but well, let's suppose you know, well, you'd need relations, so maybe you can't get there. But right, I mean, certainly, right, if you have AB plus plus A and you want to factorize it, right, you could factorize that as A times
B plus 1,
plus,
right, B plus
the identity.
Yep,
not
I understand
1.
that. Do we have that operation?
yes.
Okay, so show
Right.
it to me.
And so I think it would,
If you do collect on, I guess maybe
Just try it. Just try it.
try.
Roger, can you try that, please? Non-commutative collect of A dot B plus A. Are you typing that somewhere? I'm not seeing it.
I'm not seeing it either.
Roger, are you with us?
I'm sorry, I need to take I'm here now.
Okay, will you please type non-commutative collect of A dot B plus A?
And I guess matrix algebra.
Yeah, matrix algebra N.
Of what?
A dot B plus A. Comma, matrix algebra N.
Well, we need the A, right?
Oh, yeah.
Yeah.
Okay.
So there you go.
Great. That's an example. Okay, now I'd like to see the same thing for what you're calling free algebra with star stars. Same thing with star star with what you're calling free algebra.
Just leave.
Yeah, hold on one second.
Yeah, you don't need the argument there.
What?
You
don't need the third argument. You could just have two argument for.
Okay, fine. But that's there now.
Right, and if you did what are
okay, so what does that
composition?
mean? What does that mean? I don't understand what that means. What's that one there?
That one is the default identity.
Default identity in free algebra.
Okay, which we're representing as 1, and that. Okay.
Right, and if we
which is an unknown sized. I mean, there's no notion of size of the thing. It's just an identity element.
Yes.
What happens if I say A star star B plus 2A there with the free algebra thing? Put a 2 before the second A.
It would be 2 plus B.
Could you do that, please, Roger?
Hold on one second. What?
Put
okay,
a 2
if somebody else should share,
after,
if you can't be with us.
Sorry, what? Can you just repeat it?
Between the plus and the A, put a 2.
Okay. Now put a C. Now put C times A. Ordinary times, not star star.
Nothing will happen. Because
okay. All right. Okay. Now, how do I declare C to be a scalar variable?
So you'd have to say scalar variables goes to a list of that contains C.
Okay. Scalar variables in here.
Yep.
Mm-hmm.
In an association or what?
In an association, yeah.
Okay, now
does it need to be a list or
probably?
Probably, I think it would add list automatically.
Okay, all right. Now, isn't it the case that collect? Go look at the documentation of collect. I believe it already has a notion, does it not? So just the generic. You don't need to just generic documentation, not.
But I don't have it installed for this build. This is the prototype build. I don't have documentation locally for this build.
Okay, what function am I thinking of where you can specify what should be considered as scalars? I guess derivative, you can do that. dt.
D. Right.
dt.
You can specify constant variables. That's not commutative, it's constant variables. And,
and that's an option, right? Constant.
Yes. and then there's non-constants for D.
Okay.
And all sorts of things, all sorts of derivatives stop working when you start specifying these things, right? Because you need to make extra assumptions that you may or may not be able to make in order to finish the computations. Maybe that's irrelevant, but
well, it's might be relevant, but I mean, I don't know what's happened to the array differentiation in the case where you have what happens to array differentiation when you have all these options like constant variables and so on?
I would guess that a lot of it just returns unevaluated.
Can you comment on that, Adam?
It would hopefully work. It's implemented, but it's not thoroughly tested for on that.
Okay. Does Stefan know that that's the thing that should be tested? Can you make sure that he does?
Okay.
I'm meeting QA after this, and I'll talk to them for sure.
Okay.
Isn't it just DT that cares about that?
DT has a constants option and D has a
It's a
non-constants
non-constants
option.
Which is much hokier. The non-constants option is much hokier, in my opinion.
Yes.
Okay, so let's go back here. Can we look at the main agenda here? So if I actually let me see commutator for a second.
What?
Commutator. Can I see how that works?
Yeah. Surely there should be oh, there is the definition.
Oh, for God's sake, leave the frigging algebra out of it. Leave it out. We're not doing this. This is called, this is like, first you clear your throat and then you define 7 levels of type system and then you do something.
First of all, that should be last. That's administer trivia.
Which?
That argument. The main story is this, right? Of what it actually is.
Right. I think,
yes. So get rid of the alg thing. In the original definition, you've got to be able to say commutator of x, y.
You can.
Okay, so then why isn't that in the usage?
No, but then it's only non-commutative multiply, right? Isn't that what it means?
Correct.
Yes.
Yeah. That's not very useful. Well, I guess it is.
It is useful. It's very useful.
Right.
It's very
useful.
I mean, if you think about
commutative multiply, right?
If you think about so the Baker-Campbell-Hausdorff identity, right? How would we generate that from what we have here? Maybe that thing got renamed. Itai knows what I'm talking about, right?
It's still called that.
Which is the exponential of A non-commutative multiply B, right? Is that right?
Yep.
Yeah.
And it's the expansion of that. So show me how we would do that. And for goodness sake, there's no definition of algebras in that. It's just a thing that works for arbitrary kind of non-commutative multiplication operations. So can you show me how that would work in this setup?
Oh, I don't think we have exponentiation.
But that's a super useful thing. I mean, that's a power series with respect to a non-commutative variable, right? It's a power series.
Yes. And I guess if you want to say it's a formal power series, then yes, I suppose it could work in our framework. But X itself assumes some sort of differentiable structure, which obviously is not part of an abstract non-commutative algebra.
Right. But the whole point is that I just want to make really clear that the idea that you do the throat clearing type definition mathematical structure before you start doing operations that work perfectly well structurally is not what we want to do.
Well, this is something. Well, I mean, if you're saying you should allow a 2-argument form, I think we all agree with that. But if you're saying you can't have the 3-argument form, then
no, the 3-argument form is fine, but it is an afterthought.
We don't document
it's for
it
the
on
pedants.
top. Yeah, we just
Yes,
have
that's
it
right.
noted.
It's
Yeah,
for,
okay. So
no,
it's
no,
not
no,
a
it's
No,
on
wait,
top.
wait.
It's okay. You just list commutator of XY and then
First.
commutator of XY alg. That's all we
Fine.
need.
Yeah, yes.
Yeah.
We don't want to be doing
yes,
the type definition as the first thing we're doing.
I haven't reviewed the documentation recently. I
Yes.
would have I would
You
have
would have
made these
noted it.
notes.
Okay.
I would have made these notes to
Yeah.
Adam had I done that.
Okay, all right, fine. Okay, but I want to come back to the Baker-Campbell-Hausdorff formula.
And the other thing is that this commutator, right, it evaluates away, right? Which
Does it?
yes.
It's not obviously the right thing.
Well, yeah, I mean, I can see that for a lot of people, if it didn't evaluate, it'd be like a disappointment because they really do want it to evaluate. I mean,
Well, let's look at some use cases, okay?
sure.
For example, the Baker-Campbell-Hausdorff formula. I want to know how we get that, because that's obviously a well-known application of kind of non-commutative operations. So how do we get to that? What is the tower that we need to get to that?
Right. It's the thing that says x of a times x of b is x of b plus times x of a plus all the corrections of commutators.
Oh,
Yeah.
I know about that, but I don't know that name.
Okay. So how would we get to that from what we've set up?
What do you mean by get to that? I mean,
Well, I mean, how do I
derive
compute?
derive it? I don't think we can. I mean,
Okay. But I mean, like I have no idea. There's presumably an analog of this for the cosine function. I just don't know what it is. I've never seen it.
Sure. Right.
I would say we need symbolic operations on X and X matrix and exponentiation.
Yes. But is it so? Okay. So for example, matrix X, does it work on a symbolic n by n matrix?
Yeah. Well, it depends on what you mean by symbolic. Symbolic component-wise and symbolic as remain unevaluated that you can still operate on, like differentiate and so on, yes.
Yeah, okay. But so what I'm asking is if you say matrix X of symbolic matrix A, matrix times matrix X plus symbolic matrix B, or dot matrix X plus symbolic matrix B, then this is the thing that you should get. Then the expansion of that should be this formula. If you take the matrix log of that result, you should get this formula.
Why is that controversial? I mean, isn't that trivial result? That Z is the log of that? The matrix log of that?
No, it's in terms of the commutator. You should be able to get,
in
terms of those matrices.
So
right,
for some reason you want that.
Well, you want it in linearized, right? The whole point is that what you're doing here is instead of computing an exponential,
right. So that's right. So now you're talking about series working on a matrix X of either a symbolic matrix symbol, which is maybe something we could do, but I don't think we've gotten really to series and vector.
No, I get it. I'm just trying to understand the tower, because as we try to design the first floor of the tower, I just want to see what the tower is going to look like by the time we get to the fifth floor. So we're not designing a tower that's going to fall over by the time we get to the fifth floor.
Yep. So we need, matrix symbol of probably we want it to be NN here because we do need to specify that it's a square matrix. Otherwise, it makes no sense. And I mean, right, the left-hand side makes sense, but the right-hand side makes no sense. And then we'd need series of this to somehow, right, so we need matrix log of that thing and series of that. And that, give us the first few terms.
But we don't have a non-commutative series.
Well, I guess.
Well, is it non-commutative series or is it series working with non-commutative multiply? I think it's series working with non-commutative multiply.
Well, yes. Well, assuming that all the internal formulas don't implicitly assume that the objects commute, right? You're
Yeah,
right
I
that in
understand.
principle, in principle, yes, it's not the series that's not commutative. It's the objects being expanded. But if our formulas have
No, I
been
know
derived,
that. No, I
I
know.
mean,
But
the
this is
general array series of a function is something like this, so it's f of x, plus df of x comma x, where x can be any array. Array dot. So dot k x. If that's x0, then this is sort of x minus x0, and this is x0, and then it will keep going like this,
yeah, something like that, right? So I mean, I don't see why.
And then this is going to be dot that again.
Yeah, right.
So
I mean,
it will
it's
be a
just
power.
yes, it's just take a bunch of derivatives that a lot of different.
And this works for any array.
Yes. So fine. So I'm just saying an array, a series, you're saying that once we've defined these symbolic arrays, we should be able to do a series on operations on them. Is that true?
Yeah.
Okay. But that means we should be able to get this formula.
Well, I think it's going to be return expanded into minus dots and minus rather than the commutators.
Yes, it wouldn't do
That's correct. It won't do commutators unless we make it do commutators.
Right.
But that also relates to whether we want something which has the commutators unevaluated.
Right.
Or whether we want to unravel the commutators.
Mm-hmm.
Be interesting to see what that formula looks like if you do unravel the commutators, how much of a mess it is. I just have no idea. I've not done it. Maybe there's a simple representation of it. I don't really know.
I think this is probably going to grow quite a lot once you get into more deeper nested commutators.
Yes. I mean, there's a reason why people never write it out beyond these terms here. I mean, right, there is a formula that I don't remember, I think, that for the kth term, but it's pretty ugly, at least if you were to actually write it out.
Okay, fine. Okay. All right, so let's go back to what we were talking about before. So there's a question of whether commutator evaluates by default, which I don't think we've entirely answered here. Okay. As we look at these other operations, is there a meaningful non-commutative factor? Or is it only non-commutative collect? Is there a notion? There is a notion of factoring over non-commutative, with non-commutative operations, yes or no?
Well, there is a notion of factoring. I don't know if there is an algorithm for factoring.
So we discussed
and it's
that.
not necessarily unique, right?
No.
It's not necessarily unique. No, it's not unique. And
so we dropped that we had on the plan and it didn't kind of look interesting.
Okay, so let's take a look at the other operations you have over there on the left.
Yeah, and
sorry, one quick comment. There is a notion of commutator in group theory as well, with a very different definition. I guess if in the future we have it, we could call it group commutator. But yes, this is the ring commutator, and then there is the group commutator.
Humph.
But by that you mean conjugation, or
No. There is a commutator of G and H is G, H, G minus 1, H minus 1 in group theory. I mean, I was just looking at the Wikipedia. They have definitions in the same page.
Yes. I forgot about
the
that.
traditional commutator is this one. So this is the other one is less important, but
yeah,
but it's there too.
Cool. I mean, I think maybe we're bringing in more use cases for the future here, but for right now, this is sort of kind of the king function here.
Yes.
In a way.
Right. Yes. Yeah. And I mean, I would say that, in terms of whether commutator and anti-commutator should evaluate, right, plus evaluates, dot evaluates.
Yeah, you're probably right. Commutator should evaluate.
Yes, and we might have symbolic commutators. That we have all the other thing which kind of are then isn't useful for symbolic computation, and like we've done for the symbolic variables. So
we can always use inactive.
Yes, quite.
Yeah, I agree, but that we could have done otherwise. But I think it's just, it'd be in the same spirit, that you have a full symbolic kind of language. So there are two things I think over here. The expand, which had a small improvement where we allow second argument to be an association. The grammar base has been improved quite nicely.
We need to work on these pages.
No, I don't understand. Okay, listen. I have never, well, that's not quite true. I've almost never used a Grosvenor basis naked, so to speak. Just the
Right.
Grosvenor basis.
I'm
right?
so sorry for you.
Indeed.
So if you look at the applications, you'll see that
I'm
Adam made-
trying to, but it's empty.
Oh, really? Oh,
Yeah.
No, the applications are only on the
Non-commutative algebra page.
algebra page.
we're hoping, yeah. So you need to look at.
Uh,
They are not
Okay.
copied
Yeah,
anywhere.
Most of the time, I'm using Grosvenor bases as part of some other computation.
Yes.
And so
Yeah.
which computations will they be part of for non-commutative algebra?
Well, I mean, it's the same as kind of the linear algebra toolkit. You use it for a bunch of things. When some use case pops out that's particularly common, we build a function for it.
I know, but what are the common use cases that we
The
expect?
common
here?
use cases is simplification, proving
Okay.
identities.
Array
Right, and,
simplify.
and
So-
what we have right now is polynomial reduce and maybe monomial list. I don't know if that's
No, I mean, so you
Okay,
once you have it,
so
you use.
Are these going to be hooked up to simplify and full simplify?
They already are. Array simplify works.
To array
Yeah.
simplify.
Yes. If you scroll up a little bit on top, you'll see that the first example almost will end up with an array simplify. There you are. So you do the whole Grosvenor based routine, and then say, oh yes, you could also get the same thing by just doing an array simplify.
right. And of
Okay.
course,
So
arrays-
either, yeah,
and-
Okay, but now simplify
array simplify
itself
is
should
hooked
work
up.
on this.
it
no,
should.
no,
I
no,
think.
no. Simplify does not call array simplify. Full simplify does.
Yeah,
Okay,
whatever.
that's
Then
fine.
that's fine. One of them.
But yes, full simplify will work just as well in this case.
So that's an example which would not have worked in 14.2 without the power of the Grosvenor basis for non-commutative. So it's
I know what
underneath.
expert is. I hate these things where we have this whole giant thing where we don't know what it is.
Okay, sorry.
Okay, I can see it. It's at the top there.
Yeah.
Yeah,
I mean,
that's a
this,
nice example.
and this
That's great.
yes, this is exactly what it requires, and we've done it now. I mean, Adam has done it basically, but I think this looks like the killer app where, because it turns out all the other algebra that we have, whether Dirac or Clifford or whatever, they have matrix representations. So I'm wondering whether everything in the end should go down to matrix representations. I mean, how efficient, without actually having the matrices appear themselves, but like a dot kind of representation. So if you can do that, then we have array simplify being the master function for all those.
Well,
but
I can tell you that, for example, for gamma matrices, which, as we talked about last time, I happened to work on a bunch long ago.
Yeah.
Doing it explicitly, at least 45 years ago, was absolutely crazy.
No,
Doing
I'm
it
just saying, yeah.
explicitly and it was only worked by doing it implicitly using anti-commutators and things like this.
Right. So more thing that you could have gamma 0, not gamma 1, gamma 2, gamma 3, and then they're just pure symbols with the dot as the thing. And then I think that might be the only way you can actually compute with them with our technology.
Yes.
So I mean, okay, so maybe at some point I should remind you that if you could send us your notes or whatever, that would really motivate us, not for this release, but for the next one,
Yeah, fine. I mean, it's
Yeah.
easy enough to
So
do.
we've
If you
done
send
a
me
lot of
mail,
thinking
I'll
on-
do it.
Yeah, so
Yeah.
but it seems to me that the array simplify would be the one that is the biggest user of the Grosvenor based technology, just like solve is the biggest user of the ordinary Grosvenor basis. That's my current
Yeah.
feeling.
Okay, fine. So on this page, okay, this isn't really a guide page that you're showing me on the left.
No.
Okay, so can you show me the page on the left again? Oh, well, let's look at let's look at the usage message below non-commutative Grosvenor basis.
Oh, shit. Hold on one second.
Now, last time we talked about whether there's something that we can do that's better than the non-commutative prefix, and we didn't really come up with anything.
Yes, we gave it some thought. I think we could use associated because that's another term, but and we could have used, let's say, free, but free looks like opposite of paid. I'm not sure that, like,
Oh,
I
no,
can't
it's
review. Yeah, free doesn't look right
silly.
to us.
Free is silly.
Yeah, so I'm just saying that I think non-commutative looks like it would be up to you really, but I feel that that's the one that actually captures the real difference between this. That's my feeling, but I'll leave it to you. I did some digging as well in the literature, and it looks like And there's, I mean, maybe not
Yeah.
exactly on point, but Alok Holmes has got his whole non-commutative geometry program. I looked at his
Yes.
book also. I think it's a very modern sounding term, it's kind of,
Right.
it's
Yeah,
better
I
to,
was going to say it's the marketing term.
yeah, I
Yes,
think
all right, fine.
so.
Although this is hardly non-commutative geometry, that's a whole different level of
Well,
stuff.
yeah, I mean, that's kind of more analysis, but that's hard real analysis. I think that's the real problem over there. And we are not doing analysis over here really.
Right.
It might have some relation like with the K theory and all that, but I don't know right now.
Okay, all right. What's
Sorry,
next here?
yeah.
What's next?
You mean in terms of the main topic or just?
Are we done with non-commutative algebra?
I
you
think we are for now.
Great.
Yes.
Yeah, thanks.
Okay.
It's great.
Then, so let me just give a brief rundown.
Hold on.
Scroll.
I need to just a second. I'll be back with you in just a moment here.
Okay.
Just to check, I see anti-commutator with capital C and in other places with lowercase c.
Yeah,
It's
we've fixed
lowercase,
that.
right?
It's still getting fixed. Yeah, it should be lowercase everywhere.
Okay.
Yeah. Sorry. We know what we're just waiting for. We didn't even know whether this non-commutator would go through or not, whether it be lowercase, camel case, what, but it looks like we passed that test. Yeah. Adam, we can set up the pull request for that then with also a few modifications. I think they're waiting to start testing it.
So we do generalized power instead of
yeah.
And that's the only change right now, right?
I think so, yeah. But I think Bhunesh and Ying are waiting to start testing. So if you can do it soon and put at least one of them, maybe both, just for information, yeah, that'd be good.
Yeah.
Because we can, I don't know, it looks like we might have to hurry to get this thing merged,
Itai, what would need to happen for the generalized power to work with typesetting?
Did it respond to you, Adam?
No, is Itai here?
Okay, that's okay. You can ask it. But it's very minor. Just go ahead and put up pull request, okay? Because I think they're waiting for it. So
yeah. So I should I put up a pull request as is, or
yeah,
so there needs to be some change in the front end.
Yeah, it's okay. I think let them know
can change the name.
Let them know it's coming. Let them know. Start looking guide at the reference pages. Just to warm up. And next week we test really quickly and then merge. Hopefully. Okay. So I mean, you can tell them it's still a work in progress, but they should start looking at it.
I'm sorry. I was distracted.
So basically, we need to change the name of operational power to generalized power. So that needs to be done for the typesetting. So if you, I guess I'll do it quickly in the kernel sources and let you know so you can do the change in.
Yes, it's
wherever it needs to be done.
Yeah, it's right. I'm pretty sure I just need to change the name in one place and so yes, if you email me when you do it, I can update the front end piece very, very quickly.
Okay. Thanks.
And I'll since it does sound like these things are converging, I will ask Lou I'll open a PR even before, I'll open a PR this weekend.
Okay.
So Lou can
sorry. Hi guys. I don't have much longer here, so we may have to continue another time, but try this stuff on matrix algebra.
Okay, let me scroll all the way down. So matrix algebra is filling in things that we should have probably done 20, 30 years ago. There's more typesetting for vector matrix array stuff. There's a new integral transform, Hilbert transform.
Oh, wow. That's a friendly transform.
Oh, good. You know that. Yeah,
Mhm.
this turned the most
Okay.
interesting one. Yeah, thanks.
This one, I'm not entirely sure whether that's going in or not.
We need like a couple of weeks to decide if we have time.
Okay.
Yeah.
This is for nonlinear low order differential equations.
Yep.
There's a group of special functions,
Lomel is just
almost at the very.
Well, we already had some Lommel functions,
Well,
right?
we had a little bit in the WFR, but now we've done them all four, and they are deeply integrated into all our solvers, function properties.
What's the typical integral or differential equation which gives
You take a
one?
Bessel equation, give it a power on the right. If the power is real low, you get a Struve function. If it's higher, you get Lomel.
Oh, okay.
So, but then you got two kind of Bessel equations. So then you get like plus or minus. So you get four of these basically.
Nice. Okay. All right. Let's scroll back up again.
Okay.
Oh, no, to the matrix section.
We're there.
What is a range space?
So range space and null space are the two fundamental ways of representing subspaces.
Okay.
And null space is defined as the zero of a bunch of linear
I know.
equations.
Yeah. Right.
Yeah.
A range space is the
It's also called the
set of
column
all
space.
possible linear combinations of vectors. So it's like a parametric representation.
What is it also called, Itai?
The column space.
That's the more common.
So-
Yeah.
What name is
column-
it?
No, I mean, yeah, it has other, if you have a matrix, you often think of it as the column space because it's a set of things that you get when you multiply by a vector. And that's sort of a linear combination of the columns.
Yep.
So those two, we should have had this, I said 35 years ago, but we're adding it now. What can happen is that you have a set of columns and they're linear dependent. And what this will do is to get rid of the redundancy. So you actually have a basis.
I just do not like the name range space, partly because I just haven't heard it before.
Well, I mean, range space goes with null space. We could call it kernel and image, but we should rename
null
null
space is a fine name. Null space is a fine name.
Right.
What other, I mean, it's not the non-null space. I mean, null space is a well-known.
No, they're in different spaces. So null space lives in the, if you have a matrix.
Yeah, I understand. It lives in the space of things where it gives zeros.
Right. And so that, if you have a rectangular matrix, m by n, then the null space is a subset of Rm.
Yeah.
Okay, and this is a subspace of Rn. So I'm saying they're in different.
For other people here, am I the only person who's never heard of range space?
Well, I think this we discussed earlier. It's usually not usually, but often called column space. In fact, Gilbert's triangle has this notion of null space, column space, row space. To him, these are three fundamental aspects of matrix
Okay,
algebra.
but just following other people who are here. Itai, do you know this term?
Yes.
Me too.
Okay, fine. All right, I will consider myself either too ancient or too uneducated.
No.
So you guys are pretty sure about this name?
Yes.
Okay. Projection onto a subspace. So projection had been onto a vector, right?
Yes, and it was very hard to use with just that much. We need to have the full. And it's
so a subspace being a list of vectors, is that correct?
Exactly. Then you do like a linear combination and project onto it. Exactly. Yeah.
So it projects onto the range space of those vectors.
Mm-hmm.
So it will be some linear combination of the provided vectors, is that correct?
Yes, with the correct factor, like the correct multipliers, depending upon the actual projections onto individual vectors.
But wait a second, the result, if it's a projection of a 3D vector, for example, normally it would just give another 3D vector, but if it's projecting onto this subspace,
it'll still give another 3D
Still
vector.
give another vector.
Okay, but
Right,
it's a vector.
Right. So the
picture
vectors you
okay. In the
Correct.
range space, and now that I've learnt that word, of the collection of vectors that you gave.
Yeah.
yes,
Yeah.
Okay,
in
I
the
get it.
span, but
And that's what's left over is residual. So that's
What was the term you used? The span, what are you?
Right. You're giving a set of vectors to project into, right? So the span of those vectors is a subspace of, Rn, and then you're projecting the vector, your one vector
right,
onto
but this
that
term
subspace.
span, which I've certainly have heard,
Yeah.
how does that relate to range space? And should it be called, this? It's the
it's a matter of how you think of the input, right? If you have a matrix, right, then which is where sort of column space sort of makes sense, right? It's defined by the operator of that matrix represents. If span takes a set of vectors and gives you the set of all linear combinations of those. Whereas range space is given this matrix, which represents an operator, what are the things it eats into? I mean, which is going to be the span of the columns of that matrix.
Okay. All right. Yep.
So in particular, the dimension of a space is the length of range space.
Yep.
Okay.
Which we call what? I mean, we
don't have a name for it.
I mean, it's not the rank of the.
Yeah,
it's not. It's the matrix rank.
Yeah, it is.
Well, we have a matrix rank.
Yeah. But you often want the actual basis. This is what gives you the basis.
Right. So okay. So this is related to the matrix rank. The length of this is the matrix rank.
Yes.
Okay. Okay, that makes sense. I mean, are we sure we don't want to call it? Oh, I guess it's range space is fine.
Okay.
Yep.
So then we're adding a Frobenius decomposition. It has the same structure as a Jordan decomposition. So a Jordan decomposition is a block Jordan. It's a similarity transformation with a block Jordan matrix in the middle.
Yep.
Okay. Frobenius is almost the same thing, but it's basically block companion matrix in the middle. And the big advantage of that is that you don't introduce algebraic numbers. So you're only doing rational operations. And so for symbolic or exact computation, this is much preferable.
So just so I understand, I mean, things like LU decomposition, which was introduced in like version 1 or something.
Yeah.
I mean, it's a pretty messy object that we're returning. We're returning some kind of Fortran-esque, you know.
We want to come back to that. So since we now actually have the structured matrices that you're supposed to return, but we're not dealing with that in this release. But
okay. But are we compounding the problem by adding yet another decomposition?
No. These all return nice structured objects.
Can I see?
Yeah, sure. I think, Roger, if you go to Frobenius decomposition, even go to the neat example, you might see a really big example which will show, Stephen, the structure of
neat. Okay, I haven't seen
I just put it there because it'll be easier for us to find it. Okay, you can move it somewhere else. But you can see a way that when you're done, what you get is like these companion mate blocks, which you can think of.
What's sub 2? I just want to see the whole thing. Just show me a simple Frobenius decomposition.
Okay, if you
it's going to give a list of elements, right?
Yeah. So let's do the basics here. So this one is
so it's a pair of matrices.
Yeah. But it can probably return a block diagonal matrix.
Yes, because it is in fact block diagonal, but those are structured matrices.
Right.
But for right now, it's just returning 2 regular communal garden matrices.
Right.
Okay.
And a companion matrix, I don't know if you've seen them, but they're
I've vaguely heard of them, but yeah, tell me what they
common. Like this, okay?
The other blocks.
And there are actually sort of like 4 variants of them. This is not quite right. We'll fix that.
Well, I fixed that. I think maybe I didn't, but I think I did. Yeah.
Okay.
Okay. Is there a second argument that specifies which side?
Yes.
Yes. You
so
can
there's
see
that.
Yeah.
What is that?
Direction. And
is it left, right, top, bottom, or something?
Exactly.
Yes.
4 of them, with 2 of them being more common than the others. But we just
guys, I'm going to have to go here.
Okay.
So we got a little bit to pick up here, but otherwise we're done.
Okay.
Good stuff. Lots of nice things. Thanks a lot, guys.
Thank you.